Most high school algebra students are familiar with an easy test to determine if a quadratic equation has a non-real root. Well, and in fact, if it has one non-real root, then both of the roots are non-real. And that's by looking at something called the discriminant, which is the portion of the quadratic formula that's under the square root. And let's just quickly recall that the quadratic equation given by ax squared plus bx plus c equals 0 has a non-zero solution if b squared minus 4ac is less than 0. That puts a negative number under that radical, giving us, of course, a complex non-real number. And now I'd like to open up the following question, which is like a natural extension. And that is there any sort of similar condition to determine when an nth degree polynomial has a non-real solution? And just to keep it as simple as possible, can that condition depend on the degree of the polynomial equation as well as the first three coefficients? So in other words, we know that the polynomial looks like ax to the n plus bx to the n minus 1 plus cx to the n minus 2 plus lower order terms. And well, this is posted in a question section of the College Math Journal from 2006. Although a brief internet search will show that it shows up in a lot of different places. Okay, so let's get started. So we're going to start by using the fundamental theorem of algebra, and that says that, well, we can find n different, well, potentially different, up to the multiplicity solutions in the complex plane to this n degree polynomial equation. And furthermore, we can use those n solutions to factor the polynomial. So in other words, we can write ax to the n plus bx to the n minus 1 plus cx to the n minus 2 plus what I'll just call lower order terms as a times x minus x1 times x minus x2 all the way up to x minus xn. And I guess I should say where all of these xj's are in the complex plane, and these are the solutions to, I'll just call it our equation. And by our equation, I mean this purple boxed equation over here. And now, well, I'd like to point out that we could, re-multiply this out, and we'll quickly get a formula for, well, b and c in terms of those zeros, along with our leading coefficient of a. So let's observe that if we multiply out this right-hand side and collect the x to the n minus 1 terms, we'll come up with the following formula for b. But notice that collecting the x to the n minus 1 terms means that we're going to choose one factor from each of these to not contribute an x term for each product, and well, that'll give us all of these roots. So in other words, we get the following equation. We'll have b is equal to minus a times x1 plus x2 all the way up to xn. Okay, great. And then, well, let's observe that we could rewrite this as maybe x1 plus all the way up to xn is equal to negative b over a. That would be like another way of expressing this idea. I guess like something that I've used here but I haven't said is the fact that a is non-zero, which of course, if a were equal to 0, we'd have a lower degree polynomial, and well, we might as well just take the leading term to be non-zero. Okay, and so next up, we can do something similar with the x to the n minus 2 terms, but there we'll have to collect 2 of these root parts when we're multiplying everything out. So for instance, we'll have minus x1 times minus x2 times all of the rest x's. Or we'll have minus x1 times minus x3 times all of the rest x's. That'll give us an x to the n minus 2. So collecting all of the possible ways to do that and then equating coefficients on both sides, we'll have C is equal to A times the sum where j is less than k. And I guess I should say that j is bigger than or equal to 1 and k is less than or equal to n of xj times xk. But we can do something similar to what we did over here for this term, and we'll observe that, let's see, c over a is equal to this sum of all of the quadratic terms. Well, not quite all of the quadratic terms. Observe that we're not getting the square quadratic terms. For instance, x1 squared, x2 squared, so on and so forth. And then next up, before we really dive into the main calculation here, I'd like to present the following lemma, and that's going to say this. So if we take the sum over all j less than k of xj minus xk squared, and we get something less than 0, then in fact that tells us that there exists some sort of m between 1 and n where x sub m is not a real number. In other words, we have a non-real solution. And now, well, the proof of this is probably easier than the statement, and we're going to prove it by contrapositive. So in other words, let's suppose that we have all real solutions. So let's suppose that x sub m is real for all m between 1 and n. But that means that xj minus xk is real for all j less than k. But then if you square a real number, you can't end up with anything negative. You end up with something bigger than or equal to 0. So in other words, xj minus xk quantity squared is bigger than or equal to 0 for all j less than k. But then if we add all of those up, well, we're going to get something bigger than or equal to 0. But that tells us that the sum is bigger than or equal to 0, thus finishing our contrapositive proof. Okay, so let's maybe take the necessary stuff that we've observed on this board and, we'll summarize that next and then move on to our main calculation. So let's see what we've kind of looked at so far. We took x1 through xn to be solutions to our purple boxed n-degree polynomial equation, and then we observed that negative b over a was the sum of these roots. C over a was the sum of all possible quadratic combinations of this root. Well, almost all possible quadratic combinations. And then furthermore, we proved a fairly simple lemma that said if the sum is j is less than k of xj minus xk squared is less than 0, then, well, we have a non-real solution, which is good because we're trying to figure out when we have a non-real solution. Okay, so now the next thing that we'll do is take this sum right here, this sum as j is less than k, and I guess I should say that j is bigger than or equal to 1 and k is less than or equal to n. We'll use that, of xj minus xk squared, and we'll expand it a bit and see what we can get out of this. Okay, so let's start simply by multiplying out the terms from this sum. So that's going to give us xj squared minus 2 xj xk plus xk squared. So nothing fancy went on there. It's just a square of a binomial. So next up, I'm going to split this into 3 parts, and maybe I'll color code this. We'll have this peach underlined bit, and then this yellow underlined bit, and then also this blue underlined bit. And, well, nothing's really going to happen with the yellow underlined bit, but the 2 other parts, we're going to expand out this sum 2 different ways. So for this peach underlined part, we'll expand it out so that the k sum is inside the j sum. So let's see how we might do that. So the smallest possible value of j is equal to 1, and the largest possible value of j is n minus 1. So we see that because j has to be less than k, and k is less than or equal to n. Okay, and then let's just write the k sum now. So now the smallest k can be is j plus 1, because check it out, j is larger than k, and the largest it can be is n. And then we have xj squared. Okay, so let's maybe overline this in peach just to keep the color coding going. And now that yellow part, like I said, nothing's going to happen there. I'll bring the 2 outside, but that's all I'll do. So we've got xj times xk. And then let's do something similar for the xk bit. So now the outer sum will be the k sum, and the inner sum will be the j sum. So let's see, we'll have the sum as j goes, or as k goes from, well look, it's got to be larger than j, which is bigger than or equal to 1, so it's got to be larger than 1, so it's equal to 2 up to n. And then inside of that, we'll see that j goes from 1 up to k minus 1. And now we've got xj squared. And then, oh, well, let's keep our color coding going. So there's our yellow bit, and then here is our blue bit. But now let's observe for this inner sum, this thing that we're summing, xj squared, does not depend on j. So in fact, we're just summing xj squared for these values of k from j plus 1 up to n. Well, how many times are we adding xj squared to itself? Well, it's going to be n minus j. And we get that from n minus j minus 1 plus 1. So it's the top index minus the bottom index plus 1. So let's see, that's going to give us this. We'll have the sum as j goes from 1 to n minus 1 of n minus j times xj squared. Then I'm just going to straight bring down this middle term. I don't need to do anything with that. And let's see, for this last term, the same kind of thing's happening. So that xj squared, oh, and I realize that's a typo, that should be xk squared. So did you already make a comment? And that xk squared doesn't depend on the j, so we're just adding xk squared to itself k minus 1 times. So here we get the sum as k goes from 2 up to n of k minus 1 times xk squared. Now I'm going to take this first sum and this last sum, and well, I'm going to name the kind of dummy index from the first sum equal to k. Well, so that's just a change of index. That doesn't do anything. And then for the first sum, I'm going to take out the first term, the j equals 1 term. For the last sum, I'm going to take out the k equals n term. So that's going to give me n minus 1 times x1 squared, and then plus the sum as k goes from 2 up to n minus 1 of n minus k times xj squared. And then, well, I'm going to rearrange things a little bit. Now I'll have the sum as k goes from 2 up to n minus 1 of k minus 1 times xk squared, plus, like I promised, that nth term, which is going to be n minus 1 times x n squared. And then we've got this middle part, which I'll just tack on at the end. So that's my sum over all j less than k of xj xk. Okay, that's looking good. And now, before we move on, let's observe that we can add all of this stuff that is underlined in yellow together. So we've got n minus 1 times x1 squared, n minus 1 times xn squared. But now if we push these two together, we'll have n minus k plus k minus 1. In other words, we'll have n minus 1 times the sum of the squared of all the rest of them. So let's fit that in here, n minus 1, and now we've got the sum as k goes from 1 to n of xk squared. I'll write the index in when we move it up. Okay, so let's start from there. Okay, so this is where we ended up. And now I'm going to add something to the end of this. Well, I'm going to add 0, and I'm going to add 0 in the following form. It'll be plus minus 2n times this last sum. So that sum for all j less than k of xj, xk. And then, well, why do you want to do that? Well, that's so that we can have a 2n minus 2 times this sum. Factor a 2 out of that, and we have a 2 times n minus 1 of that sum. Okay, so let's see what we have now. So now we'll have n minus 1, and then we've got a bunch of stuff multiplied by n minus 1. We'll have the sum of all of the squares. So as k goes from 1 to n of xk squared. And then we'll have twice the sum over all j less than k of xj, xk. So that's 2 times n minus 2 of those terms. So that's going to eat up this minus 2 and that plus 2n. But that means we've got that minus 2n left over. So let's write that as minus 2 times n, and then this sum as j is less than k of xj times xk. But now the important thing here is to make a little observation on this middle term. And this is actually a multinomial that has been expanded. And this is the standard formula for the expansion of the square of this multinomial, if you will. And I'm just going to write it down. This is in fact equal to x1 plus all the way up to xn quantity squared. And you can multiply that out and convince yourselves of that if you need to. But now let's observe that we have things that look like exactly these parts up here. So observe that now we have n minus 1 times, well, that x1 added to xn squared is in fact minus b over a squared. But that's going to kill the minus sign and give us b squared over a squared. And then we'll have minus 2 times n, and then, well, notice that this next bit is exactly this c over a. So times c over a. So now, well, let's observe that we just showed that this left-hand side here was equal to this. But let's see what we can do from that. Let's notice that we can maybe multiply this whole thing by a squared, or let's point out that we really want this to be less than 0 to get a non-real solution. But let's observe that this is less than 0 if and only if the same thing is less than 0 after multiplying by a squared. You might be worried about multiplying by a squared and keeping the inequality going in the right direction, but a squared is always positive. So that's going to give us n minus 1 times b squared minus 2n times a times c less than 0. Okay, so that means we can exchange this thing right here, this sum as j is less than k of xj minus xk squared less than 0, with this object less than 0. So let's do that. Okay, so, well, after all of the calculation that we've just done, we found a partial answer to this question. We showed that if n minus 1 times b squared minus 2n times a times c was less than 0, then there exists a non-real solution. Let's just do a gut check to make sure this makes sense with our familiar quadratic formula. And we'll do that by setting n equals 2 here, and observe that this left-hand condition here becomes 2 minus 1, which is 1 times b squared, minus 2 times n, which is 4, times a times c is less than 0, which is exactly what we had before. And then, well, I guess there's an obvious follow-up question here. And that obvious follow-up question is the converse true? And I'll just say the converse is not true. And I came up with an example, but it was so easy to find an example that I thought that I'd leave it as a homework exercise. So no, and I'll just say as a homework is to find an example. And maybe you could post your example in the comments if you're psyched. And well, I don't know if there's a stronger rule that produces an if and only if statement like we have here for the quadratic equation, but if you know of a stronger rule that produces an if and only if statement, maybe also post that in the comments. And that's a good place to stop.